Hi, and welcome to day 28 of Just Start Programming. Oh, it's already day 29. My mistake. So, day 29 of Just Start Programming, the Rust programming language. So, today is another day we push forward in seriously learning Rust. And today's topic is all about the fundamentals of asynchronous programming, which is a more advanced topic for concurrency and parallel execution. So we're almost reaching 30 days. I think it's still too early to celebrate as we still need to cover a lot of topics. So let's just continue pushing forward. So join me once again live in one take, no shortcuts and no secrets. So let's just start programming. All right, so welcome back. So today we'll learn about the fundamentals of asynchronous programming. Async, await, futures, and streams. Many operations we ask the computer to do can take a while to finish. It would be nice if we could do something else while we are waiting for those long-running processes to complete. Modern computers offer two techniques for working on more than one operation at a time. So we have parallelism and concurrency. Once we start writing programs that involve parallel or concurrent operations, though, we quickly encounter new challenges inherent to asynchronous programming, where operations may not finish sequentially in the order they were started. This chapter builds on chapter 16's use of threads for parallelism and concurrency by introducing an alternative approach to asynchronous programming. Rust futures, strings, the async and await syntax that supports them, and the tools for managing and coordinating between asynchronous operations. Let's consider an example. Say you're exploring a video you have created of a family celebration, an operation that could take anywhere from minutes to hours. The video export will use as much CPU and GPU power as it can. If you had only one CPU core and your operating system didn't pause that export until it completed, that is, if it executed the export synchronously, you couldn't do anything else on your computer while the task was running. That would be a pretty frustrating experience. Fortunately, your computer's operating system can and does invisibly interrupt and export often enough to let you get other work done simultaneously. Now say you're downloading a video shared by someone else, which can also take a while, but does not take up as much CPU time. In this case, the CPU has to wait for data to arrive from the network. While you can start reading the data once it starts to arrive, it might take some time for all of it to show up. Even once the data is all present, if the video is quite large, it could take at least a second or two to load it all. That might not sound like much, but it's a very long time for a modern processor, which can perform billions of operations every second. Again, your operating system will invisibly interrupt your program to allow the CPU to perform other work while waiting for the network call to finish. The video export is an example of a CPU-bound or compute-bound operation. It's limited by the computer's potential data processing speed within the CPU or GPU, and how much of that speed it can dedicate to the operation. The video download is an example of an IO-bound operation because it's limited by the speed on the computer's input and output. IO, input and output. It can only go as fast as the data can be sent across the network. In both of these examples, operating systems' invisible interrupts provide a form of concurrency. That concurrency happens only at the level of the entire program, though the operating system interrupts one program to let other programs get work done. In many cases, because we understand our program at a much more granular level than the operating system does, we can spot opportunities for concurrency that the operating system can't see. For example, if we are building a tool to manage file downloads, we could be able to write our program so that starting one download won't lock up the UI. And users should be able to start multiple downloads at the same time. Many operating system APIs for interacting with the network are blocking. Though, that is, they block the program's progress until the data they're processing is completely ready. Note, this is how most function calls work. If you think about it, however, the term blocking is usually reserved for function calls that interact with files, the network, or other resources on the computer, because those are the cases where an individual program would benefit from the operation being non-blocking. We could avoid blocking our main thread by spawning a dedicated thread to download each file. However, the overhead of those threads would eventually become a problem. It would be preferable if the call didn't block in the first place. It would also be better if we could write in the same direct style we use in blocking code similar to this. Data equals fetch data from URL await print line data. Okay, so this one will not compile, but it's await. That is exactly what Rust async, short for asynchronous abstraction, gives us. In this chapter, you'll learn all about async as we cover the following topics: how to use Rust's async and await syntax, how to use the async model to solve some of the same challenges we looked in chapter 16, how multithreading and async provide complementary solutions that you can combine in many cases. Before we see how async works in practice, though, we need to take a short detour to discuss the differences between parallelism and concurrency. Parallelism and concurrency. We've treated parallelism and concurrency as mostly interchangeable so far. Now we need to distinguish between them more precisely because the differences will show up as we start working. Consider the different ways a team could split up work on a software project. You could assign a single member multiple tasks, assign each member one task, or use a mix of the two approaches. When an individual works on several different tasks before any of them is complete, this is concurrency. Maybe you have two different projects checked out on your computer, and when you get bored or stuck on one project, you switch to the other. You're just one person, so you can't make progress on both tasks at the same time, but you can multitask, making progress on one at a time by switching between them. Figure 17-1. The concurrent workflow, switching between task A and task B. Okay, so task A, task B, A1 to B1, B1 to A2, A2 to B2, B2 to A3, A3 continuing on to A4, and A4 to B3. Okay. When the team splits up a group of tasks by having each member take one task and work on it alone, this is parallelism. Each person on the team can make progress at the exact same time. Okay, here A1 continues to A2, continues to A3, to A4. That is task A. And then task B, you have B1 to B2 to B3. Okay, so this is concurrency and this is parallelism. In both of these workflows, you might have to coordinate between different tasks. Maybe you thought the task assigned to one person was totally independent from everyone else's work, but it actually requires another person on the team to finish their task first. Some of the work could be done in parallel, but some of it was actually serial. It could only happen in a series, one task after the other, as in figure 17-3. A partially parallel workflow where work happens on task A and task B independently until task A3 is blocked on the results of task B3. Okay. Likewise, you might realize that one of your own tasks depends on another of your tasks. Now your concurrent work has also become serial. Parallelism and concurrency can intersect with each other too. If you learn that a colleague is stuck until you finish one of your tasks, you will probably focus all your efforts on that task to unblock your colleague. You and your coworker are no longer able to work in parallel, and you're also no longer able to work concurrently on your own task. The same basic dynamics come into play with software and hardware. On a machine with a single CPU core, the CPU can perform only one operation at a time, but it can still work concurrently. Using tools such as threads, processes, and async, the computer can pause one activity and switch to others before eventually cycling back to that first activity again. On a machine with multiple CPU cores, it can also do work in parallel. One core can be performing one task, while another core performs a completely unrelated one, and those operations actually happen at the same time. When working with async in Rust, we're always dealing with concurrency. So async is always dealing with concurrency. Depending on the hardware, the operating system, and the async runtime we are using, More on async runtime shortly. That concurrency may also use parallelism under the hood. Now let's dive into async programming in Rust. Actually works. Okay. Features and the async syntax. The key elements of asynchronous programming in Rust are features and Rust's async and await keywords. A feature is a value that may not be ready now, but will become ready at some point in the future. Okay, so it got its term from some point in the future. This same concept shows up in many languages, sometimes under other names such as task or promise. Okay, so future is like task or promise. Rust provides a future trait. Future trait. Okay, so there's a future trait as a building block so that different async operations can be implemented with different data structures, but with a common interface. In Rust, futures are types that implement the future trait. Each future holds its own information about the progress that has been made and what ready means. Okay, so each future holds its own information about the progress that has been made and what ready means. So there's progress, and then probably ready is a status. I'm just guessing. Could be a status. Yeah, because it says here a value that may not be ready now but will become ready at some point in the future. Okay. You can apply the async keyword to blocks and functions to specify that they can be interrupted and resumed. With an async block or async function, you can use the await. Okay, so in async you have await. Apply the async keyword. You can use the await keyword to await a future. Again, within an async block or async function, you can use the await keyword to await a future. That is, wait for it to become ready. Any point where you await a future within an async block or function is a potential spot for that async block or function to pause and resume. Await. It means it's a potential spot for that async block or function to pause and resume. The process of checking with a future to see if its value is available yet is called polling. Okay. Aside from async, await, future, you also have polling. Polling is the process of checking with a future to see if its value is available yet. Okay. In some other languages, such as C# and JavaScript, also use async await keywords for async programming. If you're familiar with those languages, you may notice some significant differences in how Rust does things, including how it handles syntax. That's for good reason, as we'll see. When writing async Rust, we use the async and await keywords most of the time. Rust compiles them into equivalent code using the future trait, much as it compiles for loops into equivalent code using the iterator trait. So for loop is to iterator, while async and await is to future. Okay, because Rust provides the future trait, though you can also implement it for your own data types when you need to. Many of the functions we'll see throughout this chapter return types with their own implementations of future. We return to the definition of the trait at the end of the chapter and dig into more of how it works. But this is enough detail to keep us moving forward. This may all feel a bit abstract, so let's write our first async program, a little web scraper. We'll pass in two URLs from the command line, fetch both of them concurrently, and return the result of whichever one finishes first. This example will have a fair bit of new syntax, but don't worry. We'll explain everything you need to know as we go. Our first async program. To keep the focus of this chapter on learning async rather than juggling parts of the ecosystem, we've created the TRPL crate. TRPL is short for the Rust programming language. It re-exports all the types, traits, and functions you need primarily from the futures and Tokyo crates. The futures crate is an official home for Rust experimentation for async code, and it's actually where the future trait was originally designed. Tokyo is the most widely used async runtime in Rust today. Okay, so you should have searched for Tokyo yesterday. Especially for web applications. Okay, so mainly for web applications. There are other great runtimes out there, and they may be more suitable for your purposes. We use a Tokyo crate under the hood for the Rust programming language because it's well tested and widely used. In some cases, TRPL, the Rust programming language, also renames or wraps the original APIs to keep you focused on the details relevant to this chapter. If you want to understand what the crate does, I encourage you to check its source code. You'll be able to see what the crate each re-export comes from. And we've left extensive comments explaining what a crate does. Okay, create a new binary project named Hello Async and the TRPL crate as dependency. Okay, so let's follow this one. We can close this. This is already done. Then here, what do we need to do? Cargo hello async. Cargo hello async. Then cd and cargo add trpl. cd hello async. Then let's execute cargo add. Maybe let's check tree. What's under this project? Okay, source and main. Maybe let's cat cargo the tunnel. Okay, so TRPL is added here with the latest version 0.2.0. Now we can use the various pieces provided by TRPL to write our first async program. We'll build a little command line tool that fetches two web pages, pulls a title, element from each and prints out the title of whichever page finishes the whole process first. Defining the page title function. Let's start by writing a function that takes one page URL as parameter, makes a request to it, and returns the text of the title element. Okay, so this is in main RS. Code building. Oh, I think it takes a while. Maybe it's because of TRPL. Okay, so I think it's done. Can run. Can run. Oh, not yet. It's wrong. Oh, I didn't know we can run it also here. Okay, so we can replace this. And insert. So let's try to analyze. Okay, so async is something new. I think this is how you're supposed to use async. So there's a function called page title, takes in a reference to a string slice, which is the URL. It will return an option of string. Now response trpl get URL, then await. Awaiting in a future will suspend the current function's execution until the executor has run the future to completion. Suspend the current function's execution. Wait. Okay, HTML parse. No, response text. Response.text. This one also has this await. Then HTML parse. Response text. Okay, select first. Selector title. Okay, so I think this one is selecting element title. And here you have a map. What does it do? Maps an option to option. Maps an option T to option U by applying a function to contain value if some, or returns none if not, because it's an option. And then you have a closure title element, which is an element reference. Title element inner HTML. How do we know that we have element reference here? Mainly because after selecting the first one, it will return option of an element reference. select first. So this is referring to an element reference. And once you have it, this map is calculates the length of option string as an option new size. It's not clear. Okay, so we need to check the explanation. First, we define a function name page title. You can see that. And mark it with a sync keyword here. Then we use the trpl get function to fetch whatever URL is passed in and add the await. You get URL await keyword to await the response. To get the text, the response, we call it text. To get the text of the response. Okay, response, then text. And once again, await it with await keyword. Okay, then await here again. Both of these steps are asynchronous. So this and this are asynchronous. For get function, we have to wait. Okay, get function. We have to wait for the server to send back the first part of its response, which will include HTTP headers, cookies, and so on, and can be delivered separately from the response body, especially if the body is very large. It can take some time for it all to arrive, because you have to wait for the entirety of the response to arrive. The text method is also async. Text method is also async. You have to explicitly await both these features because features in Rust are lazy. They don't do anything until you ask them to with the await keyword. In fact, Rust will show a compiler warning if you don't use a feature. This might remind you of Chapter 13's discussion of iterators in the section Processing a Series of Items with Iterators. Iterators do nothing unless you call their next method, whether directly or by using for loops, or methods such as map that uses the next under the hood. Likewise, features do nothing unless you explicitly ask them to. This laziness allows Rust to avoid running async code until it's actually needed. Okay, so iterators and async features are lazy. They do nothing unless you explicitly ask them to. Okay. Note, this is different from the behavior we saw in the previous chapter when using thread spawn, where the closure we pass to another thread started running immediately. It's also different from how many other languages approach async, but it's important for us to be able to provide its performance guarantees just as it is with iterators. Once we have the response text, we can parse it into an instance of HTML using HTML parse. HTML parse. Instead of a raw string, we now have a data type we can use to work with the HTML as a richer data structure. In particular, we can use the select first method to find the first instance of a given CSS selector. By passing the string title, we'll get the first title element. So this is HTML. element in the document, if there is one, because there may not be any matching element. Select first returns an option element ref. Finally, we use the option map method, which lets us work with the item in the option if it's present and do nothing if it isn't. We could also use a match expression here, but map is more idiomatic. In the body of the function we supply to map, we call inner HTML on the title element to get its content, which is a string. When all is said and done, we have an option string. Notice that Rust's await keyword goes after the expression you're awaiting, not before it. That is, it's a postfix keyword. This may differ from what you used to if you've used async in other languages. But in Rust, it makes chains of methods much nicer to work with. As a result, we can change the body of page title to chain the trpl get and text function calls together with await between them as shown in 17-2. Okay, here you can chain it. Only one line, you get response text. This is part of the response, and all the way here is the response text. Then you have await. With that, we have successfully written our first async function. Before we add some code in main to call it, let's talk a little more about what we've written and what it means. What is in here? Title element, inner HTML. Response text. So they're asynchronous. Okay, when Rust sees a block marked with a sync keyword, it compiles it into a unique anonymous data type that implements the feature trait. When Rust sees a function marked with async, it compiles it into a When Rust function marked with async, it compiles it to a non-async function whose body is an async block. An async function return type is a type of the anonymous data type that compiler creates for that async block. Thus, writing async fn is equivalent to writing a function that returns a feature of the return type. Okay. Async fn returns a feature of the return type to the compiler. A function definition such as async fn page title in listing 17-1 is equivalent to a non-async function defined like this. Oh, okay, so you have function which is not async, but here implements feature output equals to option string. Async, and then you have move. 17-1. What is it here? Maybe it means function main. Okay. Let's walk through each part of the transformed version. Uses impl Trait syntax we discussed in chapter 10, traits as parameters here. The return trait is a feature with an associated type of output. It's a feature with an associated type of output option string. Notice that the output type is option string, which is the same as the original return type from async function version of page title. So let's check. Set again. Option string. Okay. All of the code called in the body of the original function is wrapped in a sync move block. Remember that blocks are expressions. This whole block is the expression returned from the function. This async block produces a value with a type option string, as just described. That value matches the output type in the return type. This is just like other blocks you have seen. The new function body is an async move. Where is async move? Okay, async move is here. Because of how it uses the URL parameter. We'll talk much more about async versus async move later in this chapter. Okay, so async move. So this is something new. Future output equals to option string is also something new. Okay, so here we can see the chaining approach. Text, select first title. Okay, getting the inner HTML. Now we can call page title in main. This one doesn't have main. Okay. Determining a single page title. To start, we'll get the title for a single page. Listing 17-3, we follow the same pattern we used in chapter 12 to get command line arguments in the accepting command line arguments section. Then we pass the first URL, page title, and await the result. Okay, so arguments, URL in page title, await the result. Because the value produced by the feature is an option string, we use a match expression. Page title. Page title. Option string. Okay. Over here. Okay, this is main. Okay, let's just copy this and put it here. So this is function main, which is the typical function inside main.rs. We're going to replace it with async main. Okay, so it will not compile yet. This one will not compile. Main function is not allowed to be async. Okay, main function is not allowed to be async. Here. What's the reason behind it? The reason main can't be marked async is that async code needs a runtime. a Rust crate that manages the details of executing asynchronous code. A program's main function can initialize a runtime, but it's not a runtime itself. We'll see more about why this is the case in a bit. Every Rust program that executes async code has at least one place where it sets up a runtime and executes the future. Most languages that support async bundle a runtime, but Rust does not. Instead, there are many different async runtimes available, each of which makes different trade-offs suitable to the use case it targets. For example, a high-throughput web server with many CPU cores and a large amount of RAM has very different needs than a microcontroller with a single core, a small amount of RAM, and no heap allocation ability. The crates that provide those runtimes also often supply async versions of common functionalities such as a file or network I/O. Before we proceed, let me just copy the main function. Oh, it's already here. Okay. Cannot compile yet. Okay, main function is not allowed to be async. Okay, it needs a runtime. Initialize a runtime, but it's not a runtime itself. Okay, have we read this before? Okay, we could pass vex string. Okay, so this is the version where it doesn't have async. Okay, so let's comment this out. And then insert this one. So no error. So let's compare function main. This one has async. Then here let args vex string args collect. Then here tprl run async. Okay, so here you have async moved here. Okay, let url, so it will check the first argument to be url match page title url await. So it's exactly the same as this. Get some title, then print line title for url. What's title? Non-print line url and no title. Okay. When we run this code, we get the behavior we expected initially. Okay, so maybe let's run this code. What happened? The thread main panicked. The len is 1, but the index is 1. Because I think we're supposed to pass in the first parameter. Okay, not parameter but argument. It's supposed to be this one. Okay, let's copy this. Cargo run dash dash. So this one becomes the first index. Okay, the title for https rustlang.org was Rust programming language. I think we can check that also in the browser. Let's see. Oops. Should just be this one. Rustlang. Review developer tools. Let me check. Let me put this one. It's the title. Title is here. Rust programming language. So it was able to retrieve this one. Okay. Phew, we finally have some working async code. But before we add the code to race the two sites against each other, let's briefly turn our attention back to how futures work. Okay. Each await point, that is, every place where the code uses the await keyword, represents a place where control is handed back to the runtime. To make that work, Rust needs to keep track of the state involved in the async block so that the runtime can kick off some other work and then come back when it's ready to try advancing the first one again. This is an invisible state machine, as if you had written an enum like this to save the current state at each await point. Okay, what is this? Initial, get await point, tax await point. Writing the code to transition between each state by hand would be tedious and error-prone. However, especially when you need to add more functionality and more states to the code later. Fortunately, the Rust compiler creates and manages the state machine data structure for async code automatically. The normal borrowing and ownership rules around data structures all still apply. And happily, the compiler also handles checking those for us and provides useful error messages. We'll work through a few of those later in this chapter. Ultimately, something has to execute this state machine, and that something is a runtime. This is why you may come across references to executors when looking into runtimes. An executor is a part of a runtime responsible for executing the async code. Now you can see why the compiler stopped us from making main itself an async function back in listing 17-3. If main were an async function, something else would need to manage the state machine for whatever future main returned. But main is the starting point for the program. Instead, we call the tprl run function in main to set up a runtime. Okay, so run is to set up the runtime. And run the future return by the async block until it's done. Okay, where was that? Okay, so run is a runtime. Function remains a set of a runtime. And run the future returned by a sync block. Is the sync block? Okay, so there's a future which is an async block. So the sync block is this. Okay. Note, some runtimes provide macros you can write an async main function. Those macros rewrite async fn main to be a normal function main, which does the same thing we did by hand in listing 17-4. Call a function that runs a future to completion the way tprl run does. Okay, so now let's put these pieces together and see how we can write concurrent code, racing our two URLs against each other. Okay, 17-5. We call page title with two different URLs passed in from the command line and raise them. Okay, so the main function changed a little bit. First, let's check the use of header and HTML. We have it here. Okay, so we can include HTML and header. Okay, next. Main args vec string equals to std Okay, so this is to collect the argument. Is it the same? Yeah, so they're the same. Okay. Now we have tprl run async title future one, page title first argument. Okay, so there are two page titles here. Let me copy that. Run, it should be inside run. Async, yeah. Let's put it here. Future one and future two. Okay, then here let URL maybe title is a tuple from TRPL, the Rust programming language, race title feature 1 and title feature 2, you have await. Then this one returns either left, either right. Let's copy this. So it should be after this line. URL may be title. Mismatch types. Maybe this one we can copy that. Okay. Why is it mismatched? That is maybe title. Is it because we need to complete this one first? Maybe. Let's try. Okay. So Yeah, so it's a tuple, option unknown, match. Plus to match race. What have we missed here? Found tuple, mismatch types. Option string. Vex string. Okay. Is there an error here? Mismatch types. Expected enum option string. Found tuple. URL. Don't understand why. Okay, so let's complete it first and let's see. Sync function. Page title. Is there any difference? Get. Okay, so get URL await. So this one is in one line. Title, HTML, parse, text. Select first, inner, okay. Then it will return URL. Okay. Because the return is here, URL title. So we need to comment out this one. Then this one should be fine. Yeah, TPL race. Page title. Okay. So we have changed the code. Okay, we begin by calling page title for each of the user's applied URLs. We save the resulting features as title feature 1 and title feature 2. Remember, these don't do anything yet because features are lazy and we haven't yet awaited them. Then we pass the features to TPL race, which returns a value to indicate which of the features passed to it finishes first. Oh, okay, so you have the race keyword. Who finishes first? Under the hood, the race is built on a more general function, select, which you will encounter more often in real-world Rust code. A select function can do a lot of things that TPRL race function can't, but it also has some additional complexity that we can skip over for now. Okay, so it means that instead of race, later on we use select. Either feature can legitimately win, so it doesn't make sense to return a result. Either feature, okay, let's see. Either. Where do we get left and right? What is left and right for? Okay, either left or either right. I think from the race. Left, this is left, this is right. So it's like okay, where was that? Okay, pass features to TPL race, which returns a value to indicate which of the feature passed to it finishes first. Okay. So if future one finishes first, then it will execute this part. And then if it's right, then you get this part. Left and right contains string slice and option. Because of the page title. It's a tuple. Okay. Where are we? Here. So it doesn't make sense to return a result. Instead, race returns. My mouse is jumping again. Race returns a type we haven't seen before. TRPL either. The either type is somewhat similar to result, in which it has two cases. Unlike result, though, there is no notion of success or failure baked into either. Instead, it uses left and right to indicate one or the other. Either A or B. Left is A, right is B. The race function returns left with the output from the first future argument if it finishes first, or right with the output of the second future argument if that one finishes first. This matches the order the arguments appear in when calling the function. First argument is to the left of the second argument. We also update page title to return the same URL passed in. That way, if the page that returns first does not have a title we can resolve, we can still print a meaningful message. With that information available, we wrap up by updating our print line output to indicate both which URL finished first and what, if any, the title is for the web page at the URL. So before we read this part, let's go back to the code. Okay, so if left finishes first, then the title so it's getting the title, returns the URL and then the title. Okay, if left finishes first, here you get URL returned first. Match maybe, okay, so maybe this is from the tuple. Match maybe some title, because maybe is option. So option is some and none, like what you see here. So some title print line, its page title is title. Its title could not be parsed if there's no title. URL returned first because of the race. Okay, URL returned first, and then you have match maybe title. But will it return for both? Okay, so this one, of course, we cannot run it from here. We need to pass in okay, so there's nothing we can copy here. Let's see. Nope. Okay, so there will be two arguments, 1 and 2. We can reuse this one. Run rust lang. Then maybe we pick up another one. that is mine. Maybe creates IO. Maybe not that one. Or maybe this one. GitHub Ryan. Let's check the title of the page. Developer tools. Doesn't have any title here. Title. Okay, so title is here. GitHub Ryan. Okay. Let's copy this and let's come back to our code and paste this one here. So now we have two. Okay, so here GitHub Ryan returned first. This page title is GitHub Ryan, a data is some library for Rust. Okay, so arrays is arrays. It only returned one from either of these. So if we run it again, we could get different result. Oh, it's still GitHub Ryan. GitHub Ryan. Still the same. Why? Okay, so let's pause for a break. Maybe 2 minutes break. Then we'll come back and we continue with the next chapter. Okay, I'm back. So what we will do here, let's check out other websites, because it says here you may discover that some sites are consistently faster than others, while in other cases the faster site varies from run to run. Okay, let's try cargo or maybe this one, crates.io. It's a shorter URL. GitHub versus crates.io. Okay, crates.io returned first. Its title could not be parsed. So there's no title, it seems. Okay, this time Ryan was first. Ryan, 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 Ryan. Oh, I think it's consistent. Okay, what else can we check here? So, a few things to note. We have run, which is the runtime. Then, in this case, we're testing out two futures. And then we have race here. Future 1, future 2 to check which one finishes first. And then we have await. Await. So it will only print. Oh wait, did it print the URL? It print first. Okay, so after we did this cargo run, this one returned first. Okay, what if we put something here in between? Print line. Is it async? What I wanted to try is, okay, so it will execute this, but it will wait. Will it print this immediately? Just to try out if it's asynchronous. See, tiling, building. Return first. Its title could not be parsed. Is it async? It printed last. Why did it print last? Future async run. Okay. Page title. Okay, so maybe I'm doing it wrong. Okay, maybe I'll put it somewhere here. Mm, it's not a very good example. There's a wait here. A sync page title. So what does it mean? Trying to process the information. So you have a wait here. If it executes the first function, so it's asynchronous. Returns a feature instead of blocking the current code. So it doesn't wait for it to get the URL. It continues. That's why we're seeing async here. And then once it gets the title of the page, then this one will be executed. Yeah, so I think this is the right place, just to illustrate that it's asynchronous. All right, so let's end here. Tomorrow, let's continue with the topic applying concurrency with async. All right, so hope to see you tomorrow. But first, let me thank my supporters. Have a nice day.